Hello everyone, my name is Saif. Welcome back to a new video of this series, which covers the modeling and simulation of some of the power system components. In this video, we are going to model and simulate a single-phase 3-windings transformers. The modeling of single-phase 2-winding transformers was presented in the previous video. Now, Simulink environment allows us to model multi-winding transformers, such as 3-winding transformers, where 3 coupled windings are wounded on the same core. Essentially, the operating principles of 3-winding or triple wound transformer is the same as that of the 2-winding transformers. The primary winding acts as the magnetizing winding. Its current produces the main magnetic flux. That flux links the secondary and the tertiary windings and produces EMFs in each of them, which is proportional to their number of turns. The equivalent circuit of a 3-winding transformer is shown in figure 1, which is adopted from reference number 1, and of course all the references cited in this video will be presented at the end. The equivalent circuit, primary, secondary and tertiary windings are presented. Each winding has a self-resistance presented by R1, R2 and R3, and self-inductance, which produce leakage reactance X1, X2 and X3. When load connected across the secondary and tertiary windings, current I2 and I3 flow through those windings. When there is no loads applied to the secondary and tertiary windings, where I2 and I3 equal 0, a small amount of current called I0 flows through the primary winding and feeds the transformer losses. To represent a real transformer, not only the ideal part of that transformer would be presented, in addition, the series impedances of the primary, secondary and tertiary windings exist, in addition to a shunt admittance presented on the primary side. 2 approaches will be used to model the 3-winding transformers. The first approach is to use transfer function blocks. In the second one, we're going to use the 3-winding transformer block, and the second approach is used to validate the first approach. Now, in order to find the transfer function of a linear system, these 4 steps will be followed. Now, the ampere turns equation, where the number of turns of the primary multiplied by the primary current, which equals to the number of turns multiplied by the current which goes through the secondary, in addition to the number of turns of the tertiary multiplied by the tertiary current, where equation 3 shows that the power transferred from the primary to the secondary and the tertiary windings simultaneously. Now, as I showed early on figure 1, the primary current is the sum of the no-load current in addition to the current which is responsible of the energy transferred from the primary to the other transformer terminals, I1-, and the no-load current is a product of the induced EMF in the primary winding multiplied by the shunt admittance. Now, the voltage applied to the primary winding is responsible of generating the induced EMF in the primary winding, in addition to copper losses in the primary winding due to current flowing in the series impedance. Similarly, secondary winding impedance and tertiary winding impedance are responsible of some voltage drop in the secondary and tertiary windings. When a load, an inductive load, applied to the secondary winding and another inductive load applied to the tertiary windings, the voltage across the secondary winding is equal to the current feeding that load. This is equally true to the tertiary winding, where the tertiary winding voltage equals to the tertiary current feeding the inductive load applied to the tertiary winding. Now, by listing the equations presented the 3-winding transformer and apply Laplace transform to those equations, assuming 0 initial condition, the set of equations presented by equations number 10 is presented. Now, in a similar way followed to model the two-winding transformer presented in the previous lecture or previous video, we're trying to arrange the equations to link the input voltage supply V1 to the output voltages, which is the secondary and tertiary circuits output V2 and V3. So we're trying to relate V1 to E1, the electromagnetic force in the primary winding, which links the electromagnetic force of the secondary winding and the tertiary windings, which in turn links to the secondary and tertiary windings voltages. Also, the secondary and tertiary winding currents are linked to the primary current through the turn ratios presented earlier. Now, again, the main idea is to present equations which can be written into the transfer function blocks, bearing in mind that the numerator order shouldn't be higher than the denominator. Now, in order to simulate three-winding single-phase transformers, you are using these values to define the transformer parameters: primary, secondary, series impedances, and shunt admittance. Some of those parameters have been taken from the demonstration file to simulate three-winding transformers. Again, we are modeling the three-winding transformers using two approaches. The first one is to use transfer function blocks, and those blocks have been defined in the previous couple of slides in the form of equations relating the primary voltage or the supply voltage to the secondary and tertiary voltages. The second approach is to use the existing three-winding transformer block. We just need to connect a load to the secondary and tertiary windings, measure the voltages and current. Right, so I've already started MATLAB, and now we can open a new model by either writing Simulink in the command window or by clicking the Simulink icon. So now let's go and build the circuits presented in the previous figures. Now the essential component to build this model is this block, which is a transfer function block. All right. Now when we use the small and capital letters, we have to be careful, because MATLAB is treating the same letter with capital or small as a different values or different variables. Okay, let's make it a little bit bigger. It's easier for the viewers to capture the parameters defined inside the transfer function block. Brilliant. Let's try to duplicate those blocks with a small change to represent tertiary windings instead of the secondary windings. So basically, the primary current the induced EMF in the primary is linked to the induced EMF in the secondary and the tertiary windings. Similarly, the current in the secondary windings is related to the current in the primary winding, I1 dash, and the total current flowing in the primary circuit is the summation of the current transferring energy to the secondary and tertiary windings, in addition to the current feeding the iron losses, which is multiplied by the shunt admittance to produce the induced EMF in the primary winding. And the supply voltage V1, when we subtract the induced EMF quantity from it, the resultant would be the primary current multiplied by the series impedance of the primary circuit. I guess that's all. We can, I guess, okay, so we can measure the primary current as well. Alright, so I've already write down the parameters presented in table 1, which represents a 3-winding single-phase transformer with Vs as the source voltage, 60 Hz circuit, and the rest of the series and shunt series impedances and shunt admittance, and the coefficients and the turn ratio of the primary to the secondary and primary to the tertiary windings. Right, just need to run that, and those parameters will be defined in the workspace. Then we need to run the model. I guess one second would be enough. So we have the secondary voltage V2, tertiary voltage V3, and that's what we get if we missed inputting the values of the source voltage. So the frequency we've mentioned in hertz, we need to change it to one with the radian per second. Run the model again. You can see that brilliant. So the value of the secondary and tertiary voltages is equal due to equal values of both circuits and applied loads to both of them. If you go back and check table number 1, where the inductive loads applied to both circuits have the same values. So I guess we can validate that this model is representing the transformer by using the built-in transformer block. So we need the graphical user interface, power graphical user interface. We also need the linear transformer. It's the same block we used in the previous video to model a two-winding single-phase transformer. This block have the capability of modeling two-winding transformers or a three-windings transformer. And we need to find current and voltage measurements, a single phase current and voltage measurements. Okay, so let's duplicate the load. Probably we can make this one a little bit bigger. Now the reason of building the model step by step is that these videos are for people who trying to learn how to model these power system components by themselves, or using these models to build something I guess bigger, I guess, so to speak. Can just bring this one let's duplicate those blocks. Alright, so if you go back and check the parameters presented in table 1 for the series impedances of the primary, secondary and tertiary windings, the shunt admittance parameters which present the magnetizing resistance and reactance, you will find that those parameters are equal to the parameters presented here. As I said, I've used those parameters directly from the 3-winding single phase transformer exist in Simulink library. So just check that the frequency is the same. So we've said that this is the peak, exactly the peak value of the supply voltage. So if we run the model and check, we would see that those values are similar to the values obtained from the first model. Now, to make sure that they are identical, let's put them together. Running the model again, and we can see that at the beginning there will be a difference due to different approaches of the modeling, but after very short time they will be identical. So the blue signal is coming from the transformer block. The yellow one is coming from the first modeling approach, which uses transfer function blocks, and they are identical. This is for the secondary winding voltage. For tertiary winding voltages, the situation is also the same. So the two signals are identical. You can check that even for the current, the primary current. Okay, brilliant. And with this, we go back. Okay, so with this, we conclude this video. These are the references used in this video or in this lecture. So if you like this video, please click the like button, subscribe if you like, and more topics and more videos are coming soon. Please go and check that in the description. Well, if you have been, thank you for watching.